Here is another topic for engineering physics. Let's discuss dynamics. If kinematics is the language for describing the motion of an object when a force is applied, dynamics studies the causes of motion. The two factors we need to consider to answer questions about why the motion of an object will change are the forces acting on an object and the mass of the object. Laws of motion are physical laws that are the foundation of classical mechanics. According to Sir Isaac Newton, there are three laws, which includes the first law, law of inertia, stating that every object in a state of uniform motion tends to remain in that state of motion unless an external force is applied. Take, for example, a ball on the ground. It will remain at its position not unless someone kicks it. Another is for a particle moving in a uniform velocity. Such particle will retain its motion unless an outside force is applied to it. Equilibrium of the particle is considered in the first law, whereby it says the summation of forces at an axis will remain zero. Thus, the summation of horizontal forces is equal to zero, and that of the vertical forces would be equal to zero, and also if it's going to be three-dimensional, summation of z forces would also be equal to zero. Newton's second law is known as law of force and acceleration, which states the force exerted on an object is directly dependent on its mass and is inversely dependent on its acceleration. Taking, for example, an orderly pushing a wheelchair, being empty, it would take him lesser force to gain more acceleration compared when he is pushing a wheelchair with a patient sitting. Restating, force is equal to mass times acceleration, or that would be F is equal to m times a. The third law of motion is the law of action and reaction, which states that for every action, there is an equal and opposite reaction. Either pushing or applying compressive forces, or pulling or applying tensile forces, that if forces are equal and opposite, then there would be equilibrium. The basic concepts in dynamics are the following. The first three are the force, mass, and weight, which have been introduced early in the program. Next is tension, or that would be the pulling or moving away of the force. Compression is the opposite, which would push or direct to a certain point. Normal force is taken as the reaction of a surface to the weight of any particle, and frictional force is the opposite force from the force applied dependent on the materials rubbing each other. The FBD, or free body diagram, is a graphical representation whereby the object of interest is transformed into a particle no matter its size. The forces are reflected in the diagram to clearly annotate the required. For the example of a crate pushed with a certain force, the obvious forces to be considered are the weight, directed vertically downwards, and the applied force as shown. Unseen reactions are the normal force, which is the reaction of the surface to the weight of the crate, and the frictional force, which is the reaction of the surface to the applied force. Placing all forces in the FBD would be just to reflect their magnitude and direction to the particle. So the weight is directed downwards, applied force for this example as going to the left, the normal force goes upward, and the frictional force going to the right. Take note that the frictional force is equal to friction coefficient by the normal force. For cases of tensile force, the procedure will remain the same. Figure out the forces that are acting in the situation, the weight and the normal force, the tensile force applied, and the frictional force, and then reflect them all to the Cartesian plane. So the weight would go downwards. Our tensile force would go away from the point, normal force going upwards, then the frictional force would be going opposite the direction. Take note that the tensile force will be directed away from the particle. compressive forces will be reflected similarly to the tensile forces. Thus, the weight, compressive force, normal, and frictional forces will all be transferred to the Cartesian plane as they are. So the weight would still go downwards. Our compressive force would be going to the left this time. Normal force still going upwards, and frictional force would be opposing the direction of the compressive force. And take note again that the compressive forces will always be pointing to the particle. Let's take an example for equilibrium or law of inertia. Two cables are tied together at C and are loaded as shown. Determine the tension in both cables AC and BC when the weight P is 500 pounds. We can compute for the given with any method applicable from vectors. Let us try using the triangle method as there are just three forces. So we draw the weight P of 500 pounds, then followed with the tensile forces TBC and then TAC. Be careful in drawing and make sure that they are following head-to-tail representation. Then we are going to add the angles in order to determine the interior angles. From string AC inclined as such, we can take the complement of 40 degrees inside the triangle, and then we can reflect the 50 degrees inside the triangle, completing an 80-degree angle. After completing the necessary elements of the triangle, we can use sine law. So it turns out to be 500 pounds is to sine 80, which is equal to TBC is to sine 40, and also the same as TAC is to sine of 180 degrees less 40 less 80, or that would be sine of 60 degrees. So we can directly solve for the tension at string BC as 500 times sine 40 degrees all over sine 80 degrees, giving us 326.35 pounds. And also for TAC, with 500 sine 60 degrees all over sine of 80 degrees, yielding the answer of 439.69 pounds. Using the component method, we break the forces into horizontal and vertical collinear forces. All the three forces, that would be the weight, tension at AC, and tension at BC, will be reflected from a certain point. So we can start with tension AC's components as TXAC and TYAC, and tension BC with its respective TX and TY. Then, carefully work with the angles 50 degrees for AC and 30 degrees for BC. Using the first equilibrium equation, summation of forces y is equal to 0, you can check that the resulting equation is TYAC plus TYBC less 500 is equal to 0, where both tensile forces are directed upwards, making them positive, and the weight is pointing downwards, thus negative. From previous discussion, TYAC can be computed as TAC sine 50 degrees, and TYBC would be taken as TBC sine 30 degrees. So, the first equation will be TAC sine 50 degrees plus TBC sine 30 degrees less 500 is equal to 0. The next step is to use summation of horizontal forces is equal to 0. And similarly, the resulting equation will be TXBC less TXAC is equal to 0. And solving for the components, TXAC is TAC cosine 50 degrees and TXBC is TBC cosine 30 degrees. So plugging them to the second equation, it will be TBC cosine 30 degrees less TAC cosine 50 degrees is equal to 0. And extracting TBC, we would have TAC cosine 50 degrees all over cosine 30 degrees. Simplifying, we would have 0.74 T of AC. Finally, with two equations for two unknowns, substitute TBC is equal to 0.74 TAC into the first equation, and it becomes TAC sine 50 degrees plus 0.74 TAC sine 30 degrees less 500 is equal to 0. Simplifying the equation, tension at AC becomes 438.6 pounds and tension at BC would turn out as 324.56 pounds. The deviation of answers is due to the rounding of values used in the process, comparing component method from triangle method. An example for Newton's second law is as follows. Two blocks are connected by a massless rope as shown. The mass of the block on the table is 10 kilograms and the hanging mass is 6 kilograms. The table and the pulley are frictionless. Determine the following. A. The acceleration of the system. B. The tension in the rope. And C. The speed with which the hanging mass hits the floor if it starts from rest and is initially located 1.2 meters from the floor. First is the acceleration of the system. The problem described the surface to be frictionless, thus mu is taken as 0. The formula to be used is F is equal to ma, but then remember that the force is taken as net and the mass is the total mass of the system. So let's take the FBD of the whole system starting with m2 having a weight of m2 times g, and the other mass will have a weight m1 times g, which would be reacted by the normal force, so having them cancel out, the net force will only be m2 times g. So the formula m2 times g is equal to m1 plus m2 times a, and plugging the values we get 6 times 9.8 is equal to 10 plus 6 times a, and simplify to take the value of acceleration, we would get a is equal to 3.675 meters per square second. The second requirement is the tension in the rope. In this case, we consider mass 2. It would be noted that it has its weight as m2 times g, which is pulled by the string with T, the required. So using the formula F is equal to ma, we get F net as the difference of the forces m2g minus T, which would be equal to mass 2 times acceleration. And extracting T, the equation becomes T is equal to m2g less m2a, where a is solved earlier as 3.675 meters per square second. So placing all the digits in the equation, T becomes 6 times 9.8 less 6 times 3.675, which would yield T is equal to 36.75 newtons. The third equation is the speed when mass 2 hits the floor from a height of 1.2 meters. The formula we can use is that of velocity as a function of position. Final velocity squared is equal to initial velocity squared minus 2as. Knowing that v0 is 0 and s is equal to 1.2 meters, with acceleration solved earlier as 3.675 meters per square second, we can solve the final velocity as final velocity squared is equal to 0 less 2 times 3.675 times 1.2. So, Vf is taken as 2.97 meters per second. That would be downwards. Take note that you are to take the negative out of the square root. So, the speed is taken as 2.97 meters per second. Module 4 is next with work, energy, and power.